Hello everyone, let us continue our discussion on foundation design. So we are in the 6th week and this is our 3rd lecture. So in this lecture, we will go through pile design, right? In the previous lecture, we have studied how to design shallow foundations. We have gone through the details of isolated footing and their design process. So let us take a different example. Piles are meant for transferring the load to a deeper strata, right? So if you consider a schematic diagram, so we have a column here and then there is a pile cap, and below that pile cap comes pile. When it is required, again, if the shape bearing capacity of the soil in this layer, if it is not sufficient enough, so we need to go to the deeper strata and to transfer the load here. Okay. Now there are different types of piles. In this discussion, we will talk about RC driven piles and their design. So what are the total loads transferred? It is the load coming from the column that actually is transferred to this piles. So the design of this pile actually will consider total load from the column. Then once we design that, we need to go for additional checks. Why? Because these piles are driven piles, so they are constructed and then we need to handle them, and for that we need to lift them, we need to place them at site and then drive them through the soil strata. For that, just as you can see on your screen, we have a single point lifting of the pile, and therefore the self weight of the pile acts over this length, and this will cause bending of the pile, and therefore for handling also we have to design the pile. So handling stresses, and then once we place it at the location, then we drive it, so driving stresses. So when we design, we will design the pile against all these limit states for different operating conditions. Now let us first go through the design of the pile, because that is the first objective. So case 1, where we consider the load from the column. So for this load, we design it as a column. We have already gone through column design. Now, normally the pile has a pile cap. So at this top end, it is fully fixed because it is monolithically cast, or sometimes, we have these rebars coming to the pile cap, and therefore this end is, we can consider as fixed end, while this end at the bottom we can consider it to be hinged. So L effective will be the actual length times some factor. If it is one end hinge, another end is fixed, or 0.7 L depending upon the different recommendations. So roughly it is 2/3 of the total length. Okay. Now we'll go through the design process, but once we design in a pile, first we have to provide longitudinal bars. So along the length we have to provide some bars. So these are longitudinal bars, and then as you have seen in column, we have some lateral ties, right? So this longitudinal bars should not be less than the following. First thing, it should not be 1.25% of the cross section of the piles for length up to 30 times least width. So if it is a, say, a rectangular pile, so we have the least width, say this is A, this is B, so this is the least width, and 30 times of that is the limit for the length up to which we have to provide a minimum reinforcement of 1.25%. Now if it is a circular pile, obviously it is 30 times the diameter. Next, it is 1.5% of the cross section for length up to 30 meter to 30 to 40 times least width. So if the length up to 30 times least width, we will provide 1.25%. Beyond that, up to 40 times least width, we will provide 1.5%, and 2% of the cross section for length greater than 40 times the least width. So that is the first requirement for longitudinal bars. Remember, we have to design this as a column, and you know the column design. We'll see with an example. Now, once we design the longitudinal bars, next is lateral ties or lateral reinforcement. So the guidelines for this is diameter should not be less than 5 millimeter. First requirement. Then second requirement, volume should not be less than 0.2% of the gross volume of pile. Now, near the ends, so if we again consider the schematic diagram, so this region and this region, so 3 times least width is the length where we have to provide lateral reinforcement, which is 0.6% of the gross volume. That means when we will provide lateral tie, they are not uniform throughout the length. Near the ends, they are closely spaced, and the region is 3 times the least width. So from each end, this is 3 times the least width. Say if it is A, so 3 times A is the length over which we have to provide 0.6% of the gross volume, right? Next, if the pile penetrates a hard strata, then from the top up to a length of 3 times least width from the top should have helical reinforcement. Okay, so this is an additional requirement. So we are going to provide lateral tie at the top portion here with closely spacing, and then we'll have helical bars like this will have a detailing. I will show you that. So additional helical bars we have to provide, and in addition, longitudinal bars should be held in position with spacers, and the diameter will be around dia 12 millimeter to 16 millimeter at the rate 1.5 meter, not more than 1.5 meter spacing, right? So why we need these spacers? So if you look at the cross section, let me redraw it. Let us just consider a square cross section for simplicity. So we have longitudinal bars here at the four corners, right? Now at the top, when we drive this, we need to apply a force at the top to drive it, right? That's the reason the moment you apply a force here, these longitudinal bars may be displaced, and that's the reason we need to provide spacer here, so that these bars at the top are held in position. Okay. So this type of spacer bars to maintain this geometry are provided. So these bars, these are spacer bars. These are either 12 millimeter or 16 millimeter diameter, and the spacing should not be more than 1.5 meter, right? In addition to that, we have to provide 6 millimeter links should be provided to hold the spacers. So this is an additional requirement if the pile penetrates a hard strata and we need to drive it through that hard strata. For that case, we need the additional requirement of spacers, right? Now, whenever we drive a pile, say this is the cross section, at the bottom of the pile, normally we provide iron shoes. So here, if I use a different color, here actually an iron shoe is provided so that during driving, so this is iron shoe, so that during driving, the pile head should not break. Okay, so we drive it from this end. So the moment we drive it, this head should not break, and that's the reason we have to provide this iron shoe. Now, so these are the guidelines for the design against the load coming from the column. Beyond that, as we have discussed, there are handling stresses, right? So handling stresses. Now, for precast piles, lifting using cranes, there are certain guidelines. So if the length is less than equal to 12 meter, so the pile length, if it is less than equal to 12 meter, we can provide a single point lifting. If it is more than 12 meter, then we have to provide 2 or 3 point lifting. Obviously, if we have a single point lifting, then we'll have a certain bending moment. But if we change that 2 or 3 point lifting, the maximum bending moments will change. So if the length is less than equal to 12 meter, then if this is the pile, we have a single point lifting here. Now, the pile load acts as a uniformly distributed load. So this is, say, omega. Then bending moment, Bm max, for this case is WL by 2 times L by 4, which is equal to WL square by 8. So at this critical section, we have to check the bending stress for this single point handling. If it is 2-point handling, that means length is more than 12 meter, then we have 2-point handling, and again the uniformly distributed load coming from the self weight is omega. So let this distance 2-point lifting is at x from the edge. So this is L minus twice x. Now we can easily identify the load here. This is omega L by 2 and this is omega L by 2. So maximum hogging moment is equal to omega x square by 2, and then maximum sagging moment is omega L by 2, L by 2 minus x minus omega L square by 8. This is very simple. We can easily derive that. Now, if we equate this to omega x square by 2 is equal to omega L by 2 times L by 2 minus x times, minus omega x square by 8. So if we solve it, we can find the location x, which is 0.206 L. So this is the point for lifting, if it is a 2-point lifting. So when we precast the pile, normally holes are provided at these locations. 2 holes are provided so that it can be lifted using cranes. And corresponding bending moment, if you find out, it is omega L square by 47. I leave it as an exercise. You can easily check it. So this is for 2-point lifting. Now, if it is a 3-point lifting, then you can show that x is equal to 0.15 L. So for 3-point lifting, we'll have a lifting point at the middle and 2 more on the either side, and they are at a distance of 0.15 L. And for this case, maximum bending moment is equal to omega L square by 90. Now, these are handling cases. Then, if we bring the pile at site and say this is the pile is placed like this, and then it is lifted using a force here. So this force P is for erection of the pile, and for that, this distance, that is the erection point, x is equal to 0.293 of L, and the bending moment in this case is equal to omega L square by 20. So we have to check the design of the cross section against these moments for lifting as well as for erection. Okay, these are the handling cases. Okay, so before we take an example, I repeat once more that these piles are designed as a column, and then once we design it as a column, then again we have to check for these handling stresses, which are actually design against bending, and we have already gone through the design against bending in detail, so that you can easily manage. But the point to be noted here, depending upon the length of the pile, you have to make sure whether it will be a single point lifting or 2 or 3-point lifting. Okay. Then for erection also, we have to check this capacity against the bending moment. As you can see here, it is omega L square by 23. Okay. So with that background, let us take an example. So in this example, design a pile against an axial load of 750 kilonewton. It is driven in a hard strata 8-meter deep. Use M20 and Fe 415. Okay, so now we have to design, right? So total length of the pile, including pile cap, L is equal to, it should be more than 8, so let us have it 9 meter. So try with, let us now propose a cross section. Try with 425 millimeter by 425 millimeter cross section. So now let us first check L by D. L by D is 9000 divided by 425, which is equal to 21.18, and this is more than 12. So this is a long column. For this case, L effective is equal to, it is 0.7 or 0.8. Let us consider 0.67 of L. So this is 2/3 of L, which is equal to 6 meter. Okay. Now for this long column, CR is 1.25 minus L effective divided by 48D. So 1.25, L effective is 6 meter. So 6000, which is slightly approximate, but let us take for ease of calculation 6 meter divided by 48.425. So which is 0.96. Now we have to calculate the design load PU. Design load is 1.5 times the load applied, which is 750 kilonewton, divided by CR. CR we have obtained as 0.96. So the load is 1172 kilonewton. So this is demand. What about capacity? PU capacity is, we know from our column design, it is 0.4 FCK times AG plus 0.67 FY minus 0.4 FCK times ASC. Recall we use M20 concrete and Fe 415 bars. So if we equate demand and capacity, what we have, 1172 into 10 to the power 3 is equal to 0.4 times 20 times 425 square plus 0.67 times 415 minus 0.4 times 20 times ASC. Now this first value is 1445 into 10 to the power 3 plus this first bracketed term times ASC. What you can see here, this value is more than what we have on the left hand side. That means concrete section is much bigger, so we can actually modify the cross section. So let us try with 350 millimeter by 350 millimeter. So The section is now modified. We have reduced the section because earlier 425 millimeter section is unnecessarily bigger one. So now we have 1172 into 10 to the power 3 is equal to 0.4 times 20 times 350 square plus this first bracketed term times C. So on the left hand side now we have 980 into 10 to the power 3 plus the first bracketed term times ASC. So from this expression we can solve for ASC, and if you solve it you'll get ASC is equal to 711 millimeter square. Now we also have to check the minimum requirement of steel. So for that L is equal to, we have 9000 and 30 times the least lateral dimension, which is 350, is equal to 10,500. So clearly L is less than 30 times B. So for this problem, the minimum requirement is 1.25% of the cross-sectional area. So AST minimum is equal to 1.25 divided by 100 into 350 square. So this is equal to 1531 millimeter square. So you see this is more than the AST that we have evaluated earlier, which is 711 millimeter square. So that means we have to provide this much of steel, right? So then provide 4, 5, 25. So that means A is C. Actually, this is C, not T. ASC provided is equal to 4 times 5 by 4 into 25 square, which is 1960 millimeter square. So this is okay. So let us provide 4 25 bars at the corners, and obviously the clear cover CC is equal to 50 millimeter. We'll see the detailing, but let us first complete the design. So next is lateral reinforcement. For lateral reinforcement, use 8 5 bars. Now AST lateral is 0.2% of gross volume. So volume per millimeter length is equal to 0.2 by 100 times 350 square into 1. So this is equal to 320 millimeter cube. Because we provide 8 5 bars, so A phi is equal to pi by 4 times 8 square, which is equal to 50.3 millimeter square. Now length of each tie is equal to, so if you have, this is the cross section, and inside we have the tie here with 4 25 bars at the corner. So length of the tie is 350 minus 2 times the clear cover at the either end minus 8. So this length is equal to 242 millimeter. Right. Now the volume of each tie is equal to 4 times 242 times 50.3. And this is equal to 48400 millimeter cube. So the pitch, now we can find out pitch of the tie is equal to 48400 divided by 320. Here we have obtained the volume per mm length. So this value is 151.25. So we can provide 150 millimeter center to center. So lateral tie provide 85@150 millimeter center to center throughout the length. Right. Normally the design against load from column ends here, but because for this design we have a special requirement because it is going through a hard strata, right? For hard strata, if you recall, we had some additional requirements. That means in addition to the lateral tie we have designed, at the top and at the bottom, we have to provide some additional reinforcement. So lateral reinforcement near the end. This is a additional requirement. So let us first consider top end, where we have to provide helical reinforcement, right? So length from head or from top is equal to 3 times the least lateral dimension, which is 350. This is equal to 1050. So over this length, we have to provide the helical reinforcement, right? And the volume of that helical reinforcement is 0.6% of the gross volume per millimeter of length, per millimeter of length. So what is that? This is equal to 0.6 divided by 100 times we have 350 square into 1. So this is equal to 960 millimeter. So now we can find out the pitch. Pitch is equal to circumference of spiral times Fi divided by the volume per meter length, which is 960. So circumference is pi times the dimension 242 times Fi, which is 50.3 divided by 960. So this is equal to 39.83 millimeter. So provide spiral with 30 millimeter pitch. Recall, we have to provide 6 additional bars. So with 6 additional bars of diameter, recall either 12 or 16, let us provide 16. Okay, 16 millimeter. So these are additional bar for the ties. Okay, so top end is done. Now let us go to the bottom end. So for bottom end, volume or mm length is 0.6%, which is, we have already evaluated 960 millimeter cube. So what is the pitch? Pitch is total volume we have already evaluated, which is here. So 48400 divided by 960, which is equal to 50 millimeter. So provide ties at the rate 50 millimeter center to center at the bottom. Over a length which is 3 times B. B is 350. That is, we have already evaluated this. This is 1050 millimeter. So that completes the main design against the axial load, and beyond that we have handling stress. That is the design against bending, which I can leave it as an exercise. So I leave this as a home task for you. Remember, we have derived the maximum bending moment for 2-point lifting. Recall our length is 9 meter, which is less than 12 meters. So we can go for a single point lifting. For single point lifting, this is the maximum bending moment. So you can design it accordingly, and also you have to check the bending against this value of erection. For that, we have the maximum bending moment is omega L square by 23. So this is a simple exercise which I leave it as a home task for you, right? Now finally, let us go for the detail. Now we have the main steels which are evaluated. So let us complete the detailing. For that, let us first draw the pile so the total length of the pile, as you can see here, is 9 meter. So this is 9000. Let us just put a break line here. Okay. Let us also draw the cross section. We have a square cross section, and let us draw the cross section somewhere here. So this is XX. So we have section XX. Now for this cross section, we have, these are the ties. So main longitudinal bars at the corner. So these are 525, 4 number, right? Then we have lateral ties. These are 58 at the rate 150 center to center throughout, but we'll have additional requirement at the two ends. For that, let us first draw this main bar. We'll show the helical bars in a minute, but before that, we have to provide this additional bars. These are spirals, and with 6 smaller bars inside. These are additional bars because we need to drive the pile through a hard strata. Recall, these are 16 5 bars, right? So this is the XX cross section. Let us draw another cross section because we have to show the spacer bars, right? So for that, let us take a cross section here and then say this is YY. For YY, let us copy this cross section and we will show the spacer bars. So this is section YY. Now the spacer bars are like this. Okay. They are normally like this type of spacer bars we provide. So if I show it separately, so this is the spacer bars. Okay. So we have spacer bars like this. So this spacer bar is phi 16 at the rate 1.5 meter center to center. And for that we also have links. So these are the links. So this is phi 8 at the rate 50 millimeter center to center. Now obviously we will also have the same spacer bars along the other direction. That means this direction, which I'm not drawing. Obviously we'll have the other spacer bars too, following the same specification, right? So let us not draw this, but obviously in the other direction also there will be spacer bars. Okay, let it be there as a marking along with the ties. Okay. So these are additional requirements. Now let us complete here. So we have these are the lateral ties. So phi 8 at the rate 150 millimeter center to center throughout, right? And in addition to this, we will have some helical reinforcement and the lateral ties at the bottom with a closer spacing, right? So let us show that. Now for that, we have to mark the length from the bottom. And then we have to show these bars. So these are phi 8 at the rate 50 millimeter center to center, right? And then the last one, we have to show the helical reinforcement. So that is can be shown here. So here is the helical reinforcement that we have designed because this pile is going through a hard strata. So we have phi 8 at the rate, the pitch is 30 millimeter, right? 30 millimeter center to center. Okay. So that completes the detailing part. The only thing is we have iron shoe here. So let us mark that also. So this is the iron shoe. So with that, you see, we completely show the steel requirements. One thing actually, from the top, we have to mark the region for additional reinforcement, which is again 10 1050 millimeter, 1050 millimeter, right? Okay, so with that, complete detailing is done. The only thing is we have to provide holes. Normally one hole, it's a single point lifting, so one hole should be here. Okay, it's somewhere at the middle. Okay, and then for erection also we have to provide another one, which is normally somewhere here, 0.293 of L. So these two holes should be marked. Okay, so for these two, again you have to check the handling stresses, okay, which I leave it as an exercise. So you have to check against bending, so that will complete the design of pile along with its detailing. Okay, so you have seen how we can design a driven pile, which is not difficult. The only thing is we have to keep in mind the additional requirement given in IS codal provisions, and accordingly we have to provide sufficient amount of reinforcements, right? So just go through this. If you have any difficulty, to let us know. We'll clear your doubt. So with that, our discussion on foundation design closes here. In this week, we are going to also discuss the additional detailing requirements as per Indian Standard Code, and that is ductility detailing. So in our next lecture, we'll go through the ductility detailing, what it is meant for, and what are the different provisions we have for those ductility detailing, right? Thank you very much.